Hello everyone, this is Professor Roman. Welcome to the 45th video in my video lecture series, An Introduction to Discrete Mathematics. In this video, we'll continue our discussion of graph theory with forests and trees. Graphs that don't contain any cycles are called acyclic graphs, and they are especially important in applications. So for this reason, I want to take a careful look at these types of graphs. A connected acyclic graph, such as this one pictured here, is called a tree. And a vertex of degree 1 is sometimes referred to as a leaf. So here's a leaf here. The exception I'm going to make to that statement is that a graph consisting of exactly one vertex, no edges, that's a tree, and I want to think of that lone vertex also as a leaf. The term leaf is used a little bit differently by different authors, but by now that shouldn't faze you since that's the case for a lot of this terminology. More generally, an acyclic graph of any type, connected or otherwise, is called a forest. So this picture is that of a forest. It's got three connected components, no cycles. Trees can be characterized in several ways, and it's important to go over these because sometimes one characterization turns out to be just the thing as opposed to the other characterization. But first we need a little bit of help in the form of this theorem. It says that every tree has at least one leaf. Every tree with n vertices has n minus 1 edges. Adding an edge e to a tree, T, creates a unique cycle in T, and that cycle contains the new edge, E. As to proof, for part 1, if T consists only of a single vertex, as I've said, we're going to think of that as a leaf. Otherwise, we can start at any vertex and construct a path until we can go no further. We'll get stuck at some point. And this is guaranteed by the fact that the graph has no cycles, so we can't double back on what we've already done. So eventually, since graphs are finite, we will get stuck. That final vertex has degree 1. We came into it, but we can't get out of it, so it is a leaf. As to part 2, every tree with n vertices has n minus 1 edges. This kind of begs to be proven by induction on the number n of vertices. So if n is 1, then T again is a single vertex, and there's no edges. So suppose that all trees with n vertices have n minus 1 edges, and let T have n plus 1 vertices. We have to show it has n edges. Well, we know that T has a leaf, call it V. If we remove that leaf and its connecting edge, what remains is a tree with one less vertex, n vertices. And so the inductive hypothesis tells us that has n minus 1 edges. When we put back the leaf and its connecting edge, we get T back again, and that has n edges. For part 3, suppose that T is a tree with n vertices and therefore n minus 1 edges. Then adding an edge E to T creates a graph T prime with n vertices also, but now with n edges. So T prime is not a tree. Therefore, T prime contains at least one cycle. And that cycle has to contain the new edge E because T itself had no cycles. As far as uniqueness of the cycle, if C and D were cycles in T prime, I've drawn them here, a green cycle, including the red edge, and a blue cycle, then the path consisting of the green edges and the blue edges would form a cycle in the tree T. Follow the green edges in one direction, then the blue edges in the other direction. And that's a contradiction. T is a tree, has no cycles, so the insertion of the edge E creates a unique cycle containing E. We'll also need a few facts we've seen earlier. A connected graph with n vertices must have at least n minus 1 edges. An edge in a graph G is a bridge if and only if it is not contained in any cycle. And finally, a graph is acyclic if and only if every edge is a bridge. These facts were first discussed in theorems 419 and 421. Now we can characterize trees in a variety of ways. A graph G with n vertices is a tree if and only if any of the following holds. G is connected and has n minus 1 edges, which is the minimum number of edges a connected graph with n vertices can have. G is connected and every edge of G is a bridge. G is acyclic and has n minus 1 edges. G is acyclic, and adding an additional edge to G creates a cycle containing that edge. And that cycle will be unique. G has the unique path property. Namely, there is exactly one path between every pair of distinct vertices. This is a very important property. This is my terminology. I don't know if you'll see it anywhere else. So as for proof, for part 1, if G is a tree, then it's connected by definition. And we've just seen that it has n minus 1 edges. This graph G has n vertices, therefore n minus 1 edges. So that's 1/2 of part 1. For the converse, suppose that G is connected and has n minus 1 edges. Well, if G had a cycle, we could remove one of the edges of that cycle, and the resulting graph would still be connected. We talked about that some time ago, but it would only have n minus 2 edges, and that's a contradiction to an earlier theorem that says a connected graph with n vertices must have at least n minus 1 edges. So G is acyclic, and so it's a tree. For part 2, we know that every edge of G is a bridge if and only if G is acyclic. That was right here. So part 2, G is connected and every edge is a bridge, is equivalent to saying G is connected and acyclic. And that's exactly the definition of a tree. For part 3, G is acyclic and has n minus 1 edges. If G is a tree, then it's acyclic by definition. And we have seen already that G has n minus 1 edges. So for the converse, we suppose that G is acyclic and has n minus 1 edges. We have to show it's connected. Well, if G had, say, connected components H1 through HK, we need to show that K is equal to 1. There's only one connected component. And let's say that the component H sub I has n sub I vertices for all I, from 1 to K. Then each component H sub I, being a tree, it's a connected component of an acyclic graph. So it's connected and acyclic. So it's a tree, and therefore it has n sub I minus 1 edges. Well, now we can count the vertices, which is the number of vertices is n, and that's going to be the sum of the number of vertices in each connected component. And we can also count the edges. There are n minus 1 edges. That's the sum of the number of edges in each component, which is the sum of these expressions, ni minus 1. Well, that is equal to n minus k because of this formula here. So n minus 1 equals n minus k, so k equals 1. And that means G is connected. Now let's go to part 4. G is a tree if and only if it's acyclic, and adding an additional edge to G creates a cycle containing the edge. Well, if G is a tree, then our earlier theorem tells us that adding an edge to G will create the unique cycle containing E. That's all we need. For the converse, assuming that G is acyclic and adding an edge to G creates a cycle, well, then G can only have one connected component, because if it had two connected components, you can kind of close your eyes and visualize. You've got these two blobs, the two connected components. You can insert an edge between those two components from a vertex in H to a vertex in K without creating a cycle. And that is a contradiction, so G can only have one connected component. Finally, we come to the unique path property. And we need to show first that a tree G must have the unique path property. So suppose we have two paths, P1 and P2, distinct paths from vertex U to vertex V. That's pictured here, the black edges and vertices. It kind of seems like it should be clear that we can get a cycle out of these two paths because they start and end at the same vertex. But we have to be a little bit careful because the paths may not immediately separate when they leave U or when they leave V. And that's the way I've drawn these two paths. The path P1 starts at U, goes to W, then branches along here and comes to this vertex, then goes to V. P2 also starts at U and has these two edges. It breaks away at W, comes to X, and then the same two edges here as in P1. So following the two paths, P1 and P2, starting at U, going across here to V, or starting at U, going along here to V, if you put those together, you don't get a cycle because each of the paths has these two edges and these two edges. So the round trip will traverse some edges more than once. It's not a path. It's not even a trail. It's just a plain old walk. So what you have to do is shrink these paths. Okay. So what you can do is start at U and start walking along the two paths as long as they are the same, and come to the the last vertex where the paths are the same. It could be U if the paths split right away. That doesn't matter. In the picture here, it's W. So the next vertex on P1 is up here. The next vertex on P2 is down here. In other words, they're different. You do the same thing from V. Traverse the two paths until you come to the last vertex where they're the same. So from W to X, the two paths are entirely disjoint except for W and X. Now you have a cycle. Follow, I called it R1 in this direction, then follow R2 in the opposite direction. Okay. So this isn't complicated, but there is a little trick here that you might not notice unless you give it some thought. The converse is that a graph with the unique path property has to be a tree, and I'm going to leave that for you to ponder. The unique path property has one very important application. It allows us to easily define the distance between any two vertices in a tree. It's simply the length of the unique path between the two vertices. Remember that the length of a path is the number of edges, not the number of vertices. This is a true distance function. Distance functions have four properties. Some authors would combine these into three. And I guess I better get my numbering right here. The first property is that the distance between any vertex and itself is 0. The second, called positivity, is that the distance between two distinct vertices is positive. The third is symmetry. The distance from V to W is the same as the distance from W to V. And then finally we have the triangle inequality. And I'll leave it for you, if you're interested, to confirm that this distance between vertices in a tree does have these four properties. Now, recall that a graph H is a subgraph of a graph G if the vertices of H are vertices of G and the edges of H are edges of G. Now, a special type of subgraph is one that has a full complement of vertices from the parent graph. So here's a definition. A subgraph H of a graph G is said to span G, or to be a spanning subgraph of G, if the vertex set of H is equal to the vertex set of G. In other words, they have the same vertices. So the subgraph has all the vertices of the parent graph, but not necessarily all the edges. So I guess you might say the simplest spanning subgraph of a graph G is just the graph with the same vertex set and no edges, just the vertices. That's also probably one of the most useless subgraphs, spanning subgraphs. On the other hand, a connected spanning subgraph, H of G, is a subgraph that not only includes the entire vertex set from G, but has the property that there's a path within the subgraph between every pair of vertices in the graph. Okay. And connected spanning subgraphs then are really quite important. But if a connected spanning subgraph, again we'll call it H of G, has a cycle, we can remove one of the edges of that cycle from the subgraph and still have a connected spanning subgraph. It's still connected, and we haven't changed the vertex set. So connected spanning subgraphs with the fewest number of edges are spanning trees. Here's the definition. A spanning subgraph T of a graph G that is also a tree is called a spanning tree. And here's an example that should clarify all. Here's a nice graph. This is a spanning tree. It has the same vertex set as the graph, and it's connected, but it has no cycles. Here's another spanning tree in the center here, and here's a third spanning tree. So there, in general, will be lots of spanning trees. As to the use of spanning trees, here's a simple example we'll encounter more later. Suppose that the vertices in this graph represent cities and the edges represent highways. And suppose it's your job to close as many roads as possible, subject to the condition that it's still possible to get from any city to any other city. This is certainly a practical problem, in times of small budgets and so on. How do you do this? You just choose a spanning tree and close all the other roads. Okay. And which spanning tree you choose, well, may depend on the road conditions. For example, if you've got a dirt road and all the other roads are paved, you might want to eliminate the dirt road. So that's a simple example of how spanning trees come into applications. And it's very easy to find a spanning tree in a connected graph. One way is simply to pick edges any way you want, provided that the edges you choose don't form a cycle. And when you can't pick edges any longer, the selected edges, obviously together with the vertices, form a spanning tree for G. Another way is kind of the reverse, and that is to take your graph G and find a cycle, if there is one. If there's no cycle, then since it's connected, it's already a tree, and therefore it's a spanning tree of itself. But if there is a cycle, remove one of its edges. Then take another look and see if there are any other cycles. If so, remove one of the edges on the other cycles. And keep on doing that until you can't remove edges. That will leave you with a spanning tree. So that's two different ways of constructing a spanning tree, and I'm going to leave it for you to prove that those procedures do in fact produce a spanning tree. If a graph has a spanning tree, it's got to be connected. The graph has to be connected. But the converse is also true. Any connected graph has a spanning tree, and the discussion we just had will provide a proof of that theorem. A graph G is connected if and only if it has a spanning tree. And here's another property whose proof I'm going to leave to you. If T is a spanning tree for a graph G, and if E is an edge of G that's not in T, then the subgraph we would get by adjoining that new edge has exactly one cycle C, and this cycle contains E. This we've already done, okay? But I wanted to state it again because it's relevant to the rest of the theorem. If we remove a different edge, F, from the cycle, the resulting subgraph, so that's T with E adjoined and F removed, is also a spanning tree for G. So you can swap edges basically. If you have a spanning tree and you wish that it had an edge that it does not have, put that edge in, creates a cycle, pull out one of the other edges from the cycle, and now you have a spanning tree that contains your favorite edge. And I called this the edge replacement property for spanning trees. That is my term also, so you probably won't see it elsewhere. And we will have some use for that later on. Now, the methods I've just mentioned for creating a spanning tree, they're not very systematic. They're random, pick edges or delete edges, depending on which one you're doing. But there are other methods that, although perhaps a bit more complicated, are much more useful. And so I want to discuss one of those now, probably the most famous method, at least one of the most famous, called the depth-first search. You see, there are several methods available for searching a graph in order to find a specific vertex that you're interested in, or deciding whether that vertex is in the graph. So if the graph is a graph where the vertices are cities and the edges are roadways, and you want to know, is Miami one of the vertices, you could do one of these searches for a vertex labeled Miami. Okay. And these methods are systematic, and by that I mean that if the search does not find the vertex, then you know with certainty that the vertex is not in the graph, and that you didn't just accidentally miss the vertex in some kind of random search. Okay. Two of those methods are perhaps the most famous. One is called the depth-first search, and it's relative, a cousin, you might say, the breadth-first search. Now, there's a byproduct for doing these searches, and that is if you simply let the search run until it finishes, so you're not looking for any particular vertex at all, you just want the search to run, the vertices and edges that the search traverses form a spanning tree. So using these searches to their conclusion is another way to construct a spanning tree. In the case of the depth-first search, that tree would be called a depth-first search spanning tree. And we're going to look carefully at the depth-first search. If you're interested in the breadth-first search as well, I'm going to leave that for you to investigate. I'm sure there's plenty of sources on the internet that will point you in the right direction, but you might want to try to work it out yourself after you understand how the depth-first search works. Also, for my own convenience, I'm going to refer to a depth-first search tree. We don't know yet that it is a spanning tree, but it'll be pretty obvious that it is a tree, simply as a DFS tree. And the portion of the tree that's been constructed up to a certain point, this is an iterative process, I'll call it a partial DFS tree. And so what I want to do is describe the depth first search itself and then show that the traversed subgraph is indeed a spanning tree. There are many ways to actually describe this depth first search, and I've searched some of my books and online and found different ways that authors describe the search. One of the things that disappointed me was in the small sample that I looked at, no one seemed to want to present a proof or a really convincing argument that if you let the search run to the end, what you get is a spanning tree. I was a bit surprised at that. There probably are proofs that I just didn't see. Or maybe the authors just assume that it's obvious, which it's not obvious to me anyway. So I'm going to try to describe the depth first search in some detail with some terminology you might not see elsewhere in order to be able, after I describe the search, to show you exactly why it produces a spanning tree. The unique path property is going to come into play in this discussion because it allows us to define not just the distance between two vertices, but also a relationship between the vertices. And that's often described as a parent-child relationship, so that's what I'll do. And this is illustrated here in these two graphs, but it's important to state right off that the relationships are relative to a fixed vertex, which I call the initial vertex. In some cases, it might be called a root vertex or a top vertex, but I'll use the term initial vertex. Okay, so you can see the initial vertex here at the top in both graphs. Now, as shown on the left here, a vertex V is the parent of a vertex W, and so W is a child of V, if V immediately precedes W on the unique path when it's traversed from U to W. The second to last vertex is V. Another way to say it is that there's an edge from V to W in the path going from U to W. Okay. So the parent is actually closer to the initial vertex than the child by 1 as measured by the distance. All vertices have a parent except the initial vertex. And the parent is unique. There's only one parent. But a vertex can have several children. For example, W here has 2 children. Now we can generalize this somewhat. If you look on the right here, the ancestors of a vertex V are the vertices, other than V itself, that lie on the unique path from U to V. So V has 3 ancestors, the initial vertex and these 2. The descendants of V are the vertices, like W here, again, other than V itself, for which V lies on the unique path from U to the descendant, W. So V is trapped between U and W. W is a descendant of V. So V here has 6 descendants. Now, the construction of a DFS tree, as I said before, is an iterative process. And in general, it's going to require several iterations. At each iteration, the action takes place at a single vertex. And I'll call that the current vertex. And I'll say that vertex has the focus. So at all times, there's a vertex with the focus, called the current vertex, and that's where things happen. The current vertex will change after or because of each iteration. It always changes. It's never static. To explain what the action is, the current vertex will always be in one of two states. And I couldn't think of good terms for both of them, so I'm just going to call the states open or closed. Also, each time a particular vertex gets the focus, and that may happen multiple times, the focus will leave and come back, the state of the vertex may change. So, what are open and closed? Well, a vertex is open if there's an edge emanating from the vertex, I called it V, that is not part of the partial DFS tree. So look at this picture. The black portion is the partial DFS tree. It's how much has been created so far. This edge E is not part of the partial DFS tree. Also, it does not make a cycle with the edges of T. I'll call the partial DFS tree T. So this edge here is not part of the tree and doesn't make a cycle with the tree. If it had gone from V, say, to this vertex down here, it would have created a cycle. Okay, so a vertex is open if this edge exists. Oftentimes there'll be several, but as long as there's one. And if it does exist and there is an edge, we can extend that edge to a path, and we go as far as we can until we can't go any further without creating a cycle. In other words, if this vertex here, if the only edges emanating from it go to a black vertex, a vertex in the partial DFS tree, then we're going to get a cycle. We've extended this path as much as we can, and I'm going to call it a maximal path starting at V. So by an open vertex, I essentially mean that there is a maximal path starting at that vertex. Otherwise, the vertex is closed if there's no such edge and therefore no such path. And when we do an example, you'll see exactly what's going on. I know this is a lot of terminology. At this moment, it's all kind of abstract. But as soon as we do an example, hopefully all will be revealed in its clarity. Okay. And now that we have all this terminology and preliminaries out of the way, we can describe the construction process. And after I do that, it's very short, I'll use this graph as an example of how to do a depth first search. The first step is to select that initial vertex, and you can choose any vertex you want. That gives us the parent-child relationship. I'm always going to denote that vertex by U. U gets the current focus, so here's U here on the left. It gets the current focus, and it gets incorporated into the vacuous DFS tree. There's nothing yet. So it becomes the first vertex in the tree. So the partial DFS tree at this moment is just the initial vertex. Then here is the entire description of what to do. I guess I didn't say. Or maybe I did. The initial vertex gets the focus. Okay. If the current vertex, that is to say the vertex with the focus, is closed, move the focus to the parent. Now, you can't do that if V is the initial vertex. If the focus is at the initial vertex and that vertex is closed, you're done. The construction is complete. That's how it terminates. Otherwise, if V is closed, it's not the initial vertex, you move up to the parent. Move the focus up to the parent. If V is open, then you find a maximal path, which must exist, starting at V, and add it to the partial DFS tree. So you do, and then you set the focus to the end vertex of the path. So that would be this vertex here. So you're only doing one of two things. You're either moving the focus one step closer to the initial vertex, if it's not already at the initial vertex, or you're adding paths to the tree. And then part 2 is repeat part 1 until the search is complete. You can kind of see why this is called the depth first search, because this red path, these maximal paths, go out as deeply as they can into the graph. And you can kind of imagine now what a breadth first search would be like. Rather than branching out, if you were, let's say, at this vertex, you would go one edge out in all directions, only one edge, and not a path. Okay, well then let's look at the example graph. So the initial vertex has been chosen right here and given the focus. Okay, so here we are at U, and we have to decide, is U open or closed? I guess I should look here. And it's certainly open. And there are several choices for our maximal path. This is the one I chose, U to V2 to V3 to V4. I could have gone from U to V3 to V4 to V2, and there are other choices. Doesn't matter. So we now have this green path, and we incorporate that into the depth first search tree. And we set the focus at the end vertex V4. So that's our first iteration. The second iteration now is to examine V4 to see whether it's open or closed. And there are only two other edges coming out here, but both of them form a cycle with the green path. So V4 is closed. And so the procedure says back the focus up to its parent V3. Next iteration then, V3 is open. We can take this edge. It's not part of the tree so far, the green part, the green path, and it doesn't make a cycle with the green part. So we can move along here and create a maximal path that's shown in blue. Set the focus at V7. V7 is closed. The only edge left from V7 goes back to V2, and it creates a cycle. One green edge, and it would be for blue edges. So all we can do is back up to V6. V6 is closed. So we back up to the parent V5. V5 is open. We can add this one edge path. We are now at V8. That's the current vertex. It's closed. We back up to V6, is it? V5, sorry. V5 is closed. Back up to V3. It's closed. This edge cannot be added without making a cycle. A little triangle here. Back up to its parent, which is V2. It is also closed. Back up to its parent, which is the initial vertex. It too is closed, and we are done. And indeed, the colored edges make a depth, they make a depth first search tree, and it is clearly a spanning tree. So all we are left with is justification that you always get a spanning tree from this depth first search. Well, it's fairly clear that what you do get is a tree. You're just kind of adding branches. You're not ever creating a cycle. And it's connected because you are attaching the new maximal paths to something existing, so you can get from any vertex to any other vertex along a path. The real question is, why is it always a spanning tree? Why does it always contain all the vertices of the original graph G? Well, the first thing to show, or at least one way to do this, is that every vertex in the final DFS tree, which I'll call T, must be closed. It's not initially, but eventually. When the tree is completed, all the vertices are closed. And this is how you can see that. Suppose V is a vertex and it has the focus during the construction process. If V is closed, then the next iteration requires you to push the focus up to the parent V, the parent of V. Unless, of course, V is the initial vertex, but then the construction is over. So if the construction is not yet over, you move to the parent vertex. If, on the other hand, V is open, the next iteration will add a new maximal path to the partial DFS tree and set the focus to the end vertex of that path. After that, there may follow a flurry of iterations, a bunch of iterations of both kinds, adding paths, moving up to a parent, and so on. But the graph is finite. So there can only be finitely many iterations that add new paths. That's got to stop. You're rummaging around among the descendants of V, adding paths, moving up, adding paths, moving up. The addition of paths has to stop. So eventually, you're going to be backing up till you get back to V. It can't stay, the focus can't stay in the descendants of V forever. Now when you get back to V, it still may be open, but then the same thing is going to happen. Then you have to create another path, and you'll go through possibly another flurry of iterations. But again, you'll have to return to V because of the finiteness of the graph. Eventually, you'll come back to V enough times so that V will be closed. Because each time you leave V, each time V is open, you create a new path which so to speak, eats up an edge coming out of V. It incorporates it into the tree. It's no longer available. Eventually, you have incorporated all of the edges leaving V, except the one that goes back up to the parent. And then V will be current. It'll have the focus, and it will be closed, which means the next iteration will take you to its parent. So the upshot here is that if a vertex V has the focus, whether at that time it's open or closed, eventually that vertex will become closed and the focus will pass to its parent. This is the key part of the justification. So if that went by too fast, not to worry. Stop the video or back it up or just read what's on the screen until it makes sense. Well, each end vertex, the end vertex in each path, gets the focus. That's part of the algorithm. And end vertices are always closed because they have degree 1 in the tree. There's no place to go. So according to what we just learned, then focus will move, in fact, immediately, really, to the parent of an end vertex. So now the parent of an end vertex has the focus, and this statement will tell us that eventually that vertex will become closed and focus will pass to its parent. So you can see what's happening. From the bottom up along these paths, all the vertices get closed. Every vertex then is eventually closed. Because of that, we can say that every edge in the graph G, not the tree, the graph G, that has one vertex in T must have both vertices in T, because otherwise that vertex would be open if there was an edge emanating from that vertex and it had that vertex was in T but the other vertex wasn't. You could start a maximal path from there, but every vertex is closed, so you can't do that. Now this in turn implies that T actually spans G, because if it didn't, then there is a vertex, which I'll call X, in the graph G that's not in the tree. But G is connected. And so if you pick any vertex V in the tree, there's a path from X to V. So you have a path from a vertex that's not in T to a vertex that is in T. And that means one of the edges along that path will have one vertex in T, but not the other. And that's contrary to what we just proved. So the vertex set for T is the same as the vertex set for G, and so T is a depth-first search spanning tree. Okay, that was a lot. It might take reviewing this video again, or portions of it. Hang in there. It's not really as bad as it seems the first time you go through it. Thank you for watching, and I hope to see you in the next video.